So there we go. Right, so get to grips with asyncio, or asyncio, as I will now call it forever, in Python 3. Okay, so you may be interested to know that one of the reasons the lights in London stay on these days is because of some async IO code that I wrote about this time last year, which is currently deployed onto hundreds of single board computers running in industrial facilities around London, monitoring power in industrial facilities and turning those things on and off as the electricity price goes up and down. So what I'm going to talk about today is founded on real-world experience of using this library, and I'm essentially going to replay the journey of learning that I went through when I was first getting to grips with this library in order to understand it. Of course, if the lights go out and the power goes out in the middle of this talk, we now know exactly who to blame. Those of you who are new to Python or learning Python, you might be interested in our books. Only the first one is published at the moment, Python Apprentice. It's targeted at people who can program but not necessarily in Python. My co-author, Austin Bingham, is sitting here in the front row. And we have a discount code just for you. That URL at the bottom there. So the structure of the talk today, what is async IO? Why do we care about it? Why do we need it? Why is it a thing? I'll start with that. Then we'll move on to explaining coroutines and understanding what coroutines are. They are at the foundation of how async IO works. And I'm actually going to introduce them without async IO. And in fact, we are going to build something that is largely equivalent to async IO without using async IO as a way of understanding how it works from first principles. I'm a big believer in the idea that although abstractions are great and what allow us to build fantastic systems with much less effort, you should at least understand how things are actually working one abstraction level down from where you're working day to day. Because then when things don't work quite as you expect, you have some well-founded intuition about why they are working the way they are. Then we are going to actually introduce async IO itself and move on and see some of the things that async IO layers on top of that very basic implementation. But not until the very end are we going to actually begin talking about IO in the context of async IO. So why do we need async IO? Well, I/O is high latency. I'm sure you're all aware that your computer can do a gazillion things while it's waiting for the next byte from, well, even from RAM these days. Sequential programs waste resources waiting on I/O operations. And the traditional solutions to these of multi-threading or multi-processing carry large resource overheads. Every thread on Linux is at least 8 megabytes of virtual memory stack space. And large cognitive overheads. It's hard to reason about these things when there are multiple things happening at the same time. And then we go down the rabbit hole of locking and all these difficulties that arise. And ultimately, the Python interpreter itself is shared mutable state, protected by this famous global interpreter lock. So if we use threads in Python, we are throttled by what Kevlin Henny would have us call the global interpreter bottleneck. So let's just establish a few definitions to make sure everyone's on the same page here. Concurrency is about tasks which overlap in time, but in terms of the start and end times overlap, although we're not necessarily progressing each task at any given, or all tasks at any given instant. Whereas parallelism is about actually doing things at the same time. So this is dealing with multiple things at once versus doing multiple things at once. Okay, so it's important to understand the distinction here. So async IO is about concurrency, whereas threads and multiprocesses for true parallelism require at least more than one core in your computer. So asynchronous versus sequential or versus synchronous. So asynchronous means that we don't need to wait before proceeding. We can get on with something else while we're waiting for a task to complete. Whereas synchronous or sequential means that we must complete a unit of work before we can move on to the next thing. Okay? So, of course, the overall duration of work in the sequential situation tends to be longer. It's interesting that, I find it interesting, that the word synchronous in this use is completely contradictory to the word synchronous in everyday language use. If something is synchronous in the rest of the world, that means at the same time, and we use it with opposite sense here. Asynchronous versus non-blocking. This is not really an official definition, if you like, but it's a useful distinction to make. So asynchronous tasks return immediately, often with a promise of some later result, called the future. We'll come on to those later. Whereas non-blocking functions return immediately, but they may come back with no result, a partial result, or all the result. Yeah? So the styles of programming you tend to work within these situations are different. So with asynchronous programming, we generally get a callback or a future. With non-blocking, we generally have to poll something until we actually get all of what we want. Okay, so this is an important distinction. And then down at the kind of operating system level, we can think of different ways of arranging for things to happen. We have preemptive multitasking, where the scheduler interrupts tasks. This requires that the scheduler is running continuously, so you need real hardware-level parallelism for this to work. The way operating systems do it is by using hardware timers in the CPU to trigger interrupts. Or there's cooperative multitasking, where now the tasks are in control and they must yield control back to the scheduler. But if they don't yield control back to the scheduler, the entire system hangs. Okay? So important distinctions. So async I/O is about cooperative multitasking. Yeah, so async I/O allows us to write asynchronous, concurrent, cooperative tasks. But the great thing about it is it allows us to do it in a sequential style. We don't have to think too much about the fact that multiple things are happening concurrently. It allows us to quite neatly sidestep all the problems that are usually associated with concurrency. Okay. So in the next part of the talk, we are going to introduce coroutines. I'll explain what coroutines are. I'll demonstrate how they work with Python. From now on, we've had no code so far. From now on, pretty much everything is going to be code. Okay? I'll show how coroutines are implemented in Python. And we're going to build something very similar to async I/O without using async I/O. And that will reveal to you that there is no magic, and it really is very straightforward. So to do this, we need to have some computations we can do. It's forbidden for me to use the F word in any of the presentations I give, otherwise someone will sound the Fibonacci klaxon on Twitter. So I prefer to use the Lucas sequence, which is closely related to the Fibonacci sequence. So here we have a simple generator function, Lucas, which generates the Lucas sequence. And here I'm just using itertools islice to pull off the first 10 numbers in the Lucas sequence. Okay? We need to use islice because the Lucas sequence is infinite. And this thing will happily loop forever, as you can see by the while true in here. It will never exit. So we slice off the first 10. So you're going to see me use Lucas, calls to Lucas, throughout a big chunk of this talk as a way of just having some computation to do. Now we're going to introduce a simple linear search function. This is pretty much as simple as Python gets. We have a search function which takes an iterable and some predicate function. For every item in the iterable, we test the predicate against the item and return the item. If we get to the end of the iterable without having found something that matches the predicate, we raise a value error with not found. Everybody with me? Is everybody here programming Python, or is anyone here new to Python? Okay, so it's worth me taking the effort to explain some of the Python here. So we can call search on the Lucas sequence, and we can pass our predicate, which basically says, give me the first number in the Lucas sequence which has 6 or more digits. Right? We take the number, convert it to a string, measure the length of the string. It's a cheap way. So search is just a regular function, right? There's no concurrency happening here. If we call search, it either directly returns the result or it raises an exception. Let's take search and make it into a cooperative linear search rather than a blocking search. So we'd like to search to periodically yield control to a scheduler, which we will see soon. This is very easy. All we need to do is insert the word yield here. We're not going to yield any particular result. We're just going to yield. Okay? Now, search is not a regular function. I'm also going to rename it to async search to remind us that it's now quite a different animal. So, let's import async search and Lucas, and we will invoke async search just as we did previously. I'm using a slightly different predicate here, so we don't have to run it for gazillions of iterations. We just run it for a few. So what is G? Right? G is not the thing we're looking for with the search, right? G is a generator object, right? It is an object which encapsulates that function and the running state of that function. We haven't yet started iterating that thing, but the generator encapsulates the code and the state of that particular invocation. So this is now called the generator function, and to make it run up until the first yield, we need to iterate it. And the way we iterate in Python is by using the built-in next function. So we do next G. And nothing happened. We don't get anything back. What's happened is this function has now run up to the yield, yielded nothing, and we get nothing back here. Okay, so we've just made it run one iteration of that function. Okay, now we can make it run the next iteration of that function. So each time we call next, we're doing one more loop on that search loop. Yeah. What's interesting and notable about this is that while we're progressing this function over here, we can do other stuff at the same time, right? I can print hello world now while that function is running. And then I can go back to running, advancing my search with next, next, next. And eventually, we fall off the end of the eventually we get to return item. We find the item. Now, normally in generator functions in Python, we have yield some value and return nothing. Right? We've flipped that around here. We're yielding nothing, and we're returning an item. And when you return a value from a generator function, well, generator functions that return raise what's called a stop iteration exception. And if you return a value, Python packages up the return value in the payload of that stop iteration exception object, which is kind of unexpected and weird, and very rarely used in Python, but we've just used it to actually quite good effect to make a concurrent search. Well, as you can see, this is pretty awkward to work with, isn't it? This is quite messy. But in theory, in practice, we have a concurrent search. So, async search is a generator function. Calling async search always returns a generator object. We progress the search by invoking next on the generator object. And the final result is is returned, and I use the scare quotes for real here, is returned as an exception payload. Everybody with me? Okay. Because if you're lost at this point, right, the rest of the talk is really going to be a waste of your time. Okay. So, because that's quite horrid to work with, let's wrap it up a bit into a task. So a task is this is the entirety of the code for task, right? It is a class with an initializer which accepts a routine, like the generator function we just had. We pass the coroutine to it, and it has an ID. And we keep a class ID here, which we increment each time, and we just assign the next ID to each task. So we get task 0, task 1, task 2. It's just a very thin wrapper around the routine. Now we need a scheduler to run this routine for us, because doing all this next stop iteration stuff by hand is quite fiddly. So our scheduler is very simple. The scheduler contains a queue of runnable tasks, and it contains two dictionaries which contain results from completed tasks or exceptions which have been raised by tasks which have failed. We have a function add for a routine, which is essentially a wrapper, actually wraps the routine in a task and adds the task to the queue and returns the task ID. Yeah, extremely simple. And then we have this function here, run to completion, which actually is going to run the tasks. This is kind of simple, and it has a certain elegance to it, I think. While there are tasks to run in the queue, take the first task off the front of the queue, print a message that we're about to run that task with that ID, try to run it by iterating it with next, capture the result that comes back from next. That should be none. Okay? If passing it to next raised the stop iteration, the task has finished. It has returned a result, which we need to capture from the exception. So the exception is captured as stopped. We capture the value payload from the exception and stick that into the dictionary of results for finished tasks. If we get another exception that isn't a stop iteration, something else has gone wrong, and we basically do the same again, except we stick the exception object into the dictionary for failed tasks. Okay? Else blocks on try blocks are something that's particular to Python and a bit curious. You end up in an else, you end up in a try else if the try was successful. This is the least intuitive thing in the whole language, and I just have to tell you that. So we're going to come here if we successfully iterated and it didn't return. We assert that yielded is none, because if someone's yielding something else, they're not playing by the rules we expect them to play by. We print a message, and we take the task, and we stick it back on the back of the queue. And so it will go around again. Yeah? So we always pop the task off the front, and if it needs to be iterated again, we stick it back on the other end. It has a certain elegance to it, I think. So that is the entirety of the scheduler for coroutines. Everyone okay with that? Let's go. So let's try it. Let's import our scheduler and instantiate one, and we will add our async search task on the Lucas sequence with this predicate, the first number with 6 or more digits, and call run to completion. And we only have one task, so it's just going to spin around that while loop, running task 0, next, 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 and eventually it will raise the exception and we'll capture the result here. And then we can go in and pop the result out of that dictionary. So this is for task 0, which is the only task we created. So we have a scheduler that can run one task. Woo! But of course, we can run more than one task. So using the same scheduler instance, we'll add another task. We'll just do 2 searches, one for 7-digit Lucas numbers and one for 9-digit Lucas numbers. Now when we run to completion, we alternately run task 1, 2, 1, 2, 1, 2. Task 1 completes first, we get the result. Task 2 takes a bit longer, and then we get the second result here. Okay? Nice, huh? Really simple. Concurrent execution using coroutines, implemented using Python generators. So you could do this in versions of Python going back to like 2.4 or 3 or something, yeah. Long way back. Okay, so Lucas numbers is fine, but we need, to really demonstrate this, we need some slightly heavier computation, and also to demonstrate some problems you run into with concurrent programming, we need some heavier computation. So here's my noddy primality testing function. Don't use this for real. It's horribly inefficient, but that actually helps in this case. And of course, it works as you would expect. We can test primality of numbers. The point about this is because it's horribly inefficient, although I can test the primality of that in like half a second, testing the primality of that takes half a week, right? It takes a long time, right? I have to, maybe not half a week, but I have to run through 1.5 billion numbers for this to return true. which takes a while. Python is not a fast language. Okay, here's another coroutine. This is very similar to the search coroutine, except it prints all the matching results. Okay, so we're just looping around. Anything that matches, we print that we found an item, and we yield to the scheduler. Yeah, so we're just going to loop through the sequence. So here we go. We import async print matches is prime and Lucas. We set up the scheduler. We add a task. So print all the numbers from the Lucas sequence which are prime. Okay, and off we go. We get 2, 4 is not prime, 3, etc. We get prime numbers, with, of course, increasing gaps as we go up the sequence. Okay, so that was one. This is one task running, just task 0 there. Now we want another message, another task to run. So I've cooked up this task here called repetitive message. And all it does is it prints a string at some time interval. Yeah. So infinite loop, this task never completes, just runs forever, prints the message, and then this is basically a sleep, right? We just wait until the duration expires, then we break out of the inner while loop and go around again and print the message again. Very straightforward. To make this cooperative, we just need to add the yield in the inner loop. Okay? And being good citizens, we'll rename it as async repetitive message. There's a subtle bug here. If the interval is a very small number, like 0, right, this will never yield, right? Because you'll come in here, break, go back here, come back to here, break, and you'll never get to this yield. You have to be really quite careful about where you yield control. You need to yield control there. You need to ensure that all your coroutines, and even though I'm not writing async IO code, this rule applies to async IO, you need to ensure that all your coroutines yield, well, either return a result immediately or yield. Yeah? So you need to be quite careful about the control flow here and make sure you're yielding at least once. Otherwise, you'll hang the whole system. So we need to get this yield in the right place, which is there. So let's see this running. So we'll import the stuff we need, instantiate a scheduler, schedule a task. I spend a lot of time in airports. If I'd recently been through Schiphol, this would say, mind your step. Okay, so we've set up a unattended baggage will be destroyed every 2.5 seconds, and we're going to calculate primes from the Lucas sequence concurrently. Run to completion. Let's go. We get our message after 2.5 seconds. There was one at the beginning as well. But now we've stopped getting our messages. Right? We should be getting unattended baggage will be destroyed every 2.5 seconds, but we haven't. We're stalled on task 0 here. What's going on? Now, eventually we get one after a very large prime number, right? That's because determining the primality of large numbers takes a long time. And even though our search function is concurrent, our primality testing function is not. It's blocking, right? So we've committed a great sin here in concurrent programming of invoking a blocking function, right? And the whole system has to wait for that to complete. So, there we are. Async print matches is non-blocking, but is prime blocks on large numbers, stalling the whole system. So we need to fix that. So we've just discovered a rule, really, which is that everything you call transitively from a coroutine should be non-blocking. Okay? Everything. Because if you call anything blocking in the entire call stack, you're going to hang the whole system. So coroutines are contagious to callees, is one way of looking at that, right? Okay, so let's fix our isPrime function. So here's the original isPrime on the left, and calling this returns a bool, true or false. Here's async isPrime, which is exactly the same thing, except now we have a yield in this loop, right? And calling this, of course, returns a generator object, so we need to iterate it with next, and it will work with our scheduler. We also need to fix every call site of isPrime. Because calling it returns a generator, we cannot just call it, we have to iterate it. And the way we call nested generators from generators is with yield from, which, if my memory serves me correctly, is Python 3 only. Yeah? If you did this in Python 2, you'd have to write an explicit for loop here to iterate that thing. Okay, so this avoids us having to put an extra for loop in here. So now we're using yield from. Because we're using yield from, which eventually is going to, our async predicate in this case is async isPrime. Because we have this yield from and this yield here, we no longer need this yield here. So this is a term I've invented, bare yield, right? You don't need it in this case, as long as you are yielding to another coroutine that you're delegating to. Okay, so we can get rid of the bare yield. I'll come back to this term bare yield in a minute. So this is the second rule, which is that everything that calls transitively your coroutine must iterate the generator. So not only are coroutines contagious to callees, they are contagious to callers. And of course, you don't have to think about this very hard to realize that very soon your entire program needs to be asynchronous except for the main function. Right? That is logically where you end up. Yeah? Or at least, if not asynchronous, at least non-blocking. Right? So it's very hard to take an existing system which is not written in this style and turn it into a system written in this style. This is a good thing to adopt at the beginning, right? But you're going to have a pretty hard time refactoring your way from whatever you have to something that works like this because of this contagious viral property of asynchronous programming. So here's another case where this contagious thing crops up. So we had async repetitive message here, which basically printed a message and then had a sleep. So this thing here is sleep, effectively, right? So let's do a nice refactoring and extract an async sleep function, or extract generator refactoring. So here we've extracted that, all the code except the print, into async sleep, which is here. This now has the bare yield, and we can yield from async sleep here. Okay, so that's just a straightforward extract function or extract method refactoring done with generators. Okay, so rather than a call, we have to use yield from here. Make sense? Following? Good. So this sleep thing turns out to be significant. So async sleep always yields at least once, because that's one of the guidelines I gave you. Right? We come in here, and you always get to that yield at least once. Async sleep 0 yields exactly once, right? Which is nice, a useful property. So because of this, any occurrences of bare yield anywhere else in our system can be replaced with yield from async sleep 0. And that means the only bare yield we need in the entire system can live inside the sleep function, right? Which further means that if the async sleep function is provided to you by the scheduler, you don't need any bare yields anywhere in your system, right? So the only bare yield then can live inside the scheduler itself. So by applying this replacement of bare yield with async sleep, we can take all the other code we've written so far, we can find all the bare yields, there's one here and one here, and we can replace them with yield from async sleep 0. Now, you just think, well, okay, I've just added some code to no effect. Well, actually, that's going to turn out to be important in a refactoring that's coming soon. So just to prove to you that it was actually a refactoring and we haven't changed the behavior of the system one iota, we will run it again. We'll set up our repetitive message. Remember, now we have async is prime rather than is prime. Run to completion. We get our prime numbers, and we should keep getting our repetitive message now because is prime is no longer blocking. Yeah? So this will keep going. And I think for the next one we have to wait like half an hour. So I'm not going to do that. You do have to wait a while. Okay. So we're about halfway through, I guess. Yes, exactly halfway through, which is great. So we've got this far without mentioning async IO, but I've actually built something that does exactly what async IO does. I just haven't used all the new fancy keywords that we get in Python 3.5 and 3.6. In fact, what I've shown you is very close to how async IO is used in Python 3.4 before they introduced the await and async keywords. Okay. So knowing what I've just shown you, you could any Python 3.4 code will look very familiar. And in fact, what I have shown you is so closely equivalent to async IO, I can actually programmatically refactor what I've written into real async IO code, or mechanically refactor. So let's do that. So there's all the code I've shown you so far. On the right here, I'll show you the refactoring steps. So the first thing we do is we're going to take any time I've written def async underscore foo, and we're going to refactor that to async def foo, which is a new keyword in Python. Okay. So now we have async def. This is a way of declaring a coroutine in Python 3.5 and onwards. Next thing is, of course, I'm going to import async IO up there. There it is. Now I'm going to replace my calls to async sleep, my own sleep function, with calls to async IO dot sleep, which is the library provided function. So we do that refactoring. Now, because I'm calling the library sleep, I don't need my sleep anymore. We can get rid of that. That's gone. Finally, we can replace any occurrence of yield from with await, which is a new keyword in Python 3.5 and onwards. And behind the scenes, Python is working exactly the same way with iterators and generators and all these things, right? So that's all that async and await are doing. The only thing they do over and above that is they actually give the functions slightly different types, so Python knows they are awaitables. So that is now legitimate Python 3.5 or 3.6 code. So let's run it in Python 3.5. Slight differences here. I have to get the async IO event loop now, rather than creating my own scheduler. I don't need my own scheduler anymore. The async IO event loop is Python's scheduler. Instead of using scheduler.add, I now do create task. I'm going to come back to tasks in a bit and explain what an async IO task is. So we create two tasks. That actually adds them to the scheduler. It doesn't just create the task object. It actually schedules it with the scheduler. Slightly confusing naming. Then we're going to run our scheduler forever, and we get the same result, just like we had with our own code. I'm not going to make you wait for the next large prime. Okay, so let's get into some more details of what async IO, of some of the things we've established about async IO by building a fake. asyncio. So coroutines implement tasks. Coroutines await other coroutines. The event loop schedules concurrent tasks. Tasks must not block. If you task blocks, everything blocks. By awaiting another coroutine, you facilitate a context switch. Every time you do that, every time you use await, that is an opportunity for the scheduler to run another task. They might decide to run your task again, especially if it's the only task. But that is the opportunity for the scheduler, the event loop, to intervene. And if you want to yield control without needing a result from the thing you're yielding from, the way to do that is asyncio sleep, 0. Okay? That just says, I want to yield control, let somebody else have a go. Let another task have a go. A word on terminology. This gets a bit confusing. This is a coroutine. It's the code. It's made of code, and it's callable, right? We can call this. The thing we get back when we invoke the coroutine is a coroutine object, right? You might not like this terminology, but it's the terminology that Python has settled on in the documentation. So this is the code, and it's callable. This is the running code, and its execution state, and it's awaitable. This is a new word in Python terminology. So the coroutine object is awaitable. So very often we want to monitor a running task. The tasks we've seen so far, you can't monitor them in any way. You just have to run them and wait until they are complete. Sometimes we want dependencies between tasks. We want one task to report on the progress of another task, or we want a task to wait for another task to complete. So the most basic way we have to do that is a thing called a future. So let's look at the code we have here. I've just taken our search function and I've modified it to accept a future object. We'll come on to what that is in a moment. And all my monitored search does is delegate to this regular search function we had earlier, this regular search coroutine we had earlier with await. So we try this. If the search fails, we call a method on the future called setException with the exception value. Else, the try has succeeded, we set the result, the found item in the future. Okay? So the future is an object which encapsulates the idea of a potential future result, an IOU, if you like. And then we have another task here, monitor future, into which we can pass the same future, and we're just going to loop around reporting on whether that future is done yet every few seconds. Okay? So in the main code here, we get the event loop, we create a future using this factory function on the event loop. I set up my monitored search, looking for the first 13-digit prime. That takes a while. And add the coroutine object that comes back from that invocation to the event loop as a task. Here I create another task using monitor future, and I pass the same future instance here. So I'm creating the future here. I pass the same future into the monitored search and into this monitor future task. Okay? And then I run until complete. Off we go. And we get waiting, reported from the monitor future task until the monitored search returns its result. Okay? We then get a warning from asyncio event loop saying, hang on, you've terminated the event loop here with loop close, but there are still running tasks. You probably don't intend to do that. Okay? So even though our monitor future says while future not done and should wind itself up when the future is done, it never gets opportunity to wind itself up, right? Because we exit as soon as the future is complete. Okay? So this final iteration of this loop never gets to happen. So we'll come back to fixing this error in a bit. We'll just leave it there for now. Future, there is a class called future in asyncio. You should avoid calling the future constructor directly. you should always go via the create future factory function on the event loop you're using. The reason for that is that different event loops will specialize the future implementation, okay? So at the very least, Windows and Unix use different event loop implementations, right? So you should always go via the factory function. So now we're going to have a task. And a task in Python asyncio is obviously it's a very fundamental thing. We use them all over the place. I've been creating tasks already. I think the documentation for what a task actually is awful. It's dreadful. So, I mean, the documentation says something like a task wraps a coroutine in a future. And that's just very ambiguous to me. So this is a picture of what a task actually is. It's a subclass of future. So it literally is a future, and it has a reference to a coroutine. This is a really terrible use of inheritance in the design of the language. It never makes sense to call setResult or setException on a task. Right? That should not be available to anyone who has a handle on a task except the scheduler. So I think it's really not good design. But that's how it is, and we have to live with it. I think it's a well-known fact that the people who design Python don't really understand object-oriented programming in some sense anyway. So it's perhaps no surprise. Yeah. Well, it's in the Python standard library. So it is, I mean, well, this could contain a future rather than being a future, right? Yeah. So. Well, the future could be a implementation detail hidden as far as we can hide things in Python, right? So, I mean, nothing's private, right? This is Python. We're all grown-ups here, so. So because the task is a future, we can monitor the search task directly now rather than having to create our own future object separately, okay? So, and when we do that, we get exactly the same result as before, but we still haven't solved this problem of the task being destroyed, the monitor future task being destroyed prematurely. Another very confusing naming thing in the library is how you should create tasks. For the same reasons as futures, you shouldn't call the task constructor directly. You should prefer to call the create task factory on the event loop. That allows the event loop implementation to specialize the task. Even better, though, you should call ensure future instead. Ensure future actually calls this. And I find this name very confusing. It's more general. It doesn't just accept coroutine objects, it accepts any awaitable object, which is a new concept in Python. And you must pass the event loop to it. It's also idempotent, so you can pass the same thing to it several times, and it will only wrap it up once in a task. So this is the preferred way to create a task in Python, ensure future. Yeah, in spite of its confusing name, it does return a task. So there we are. We create the tasks. So we still haven't dealt with the fact we're not cleaning up one of our tasks gracefully. So to do that, we can wait on more than one task. So we use an asyncio function called gather, which takes any number of awaitables. So here, and this returns a future. So here I'm gathering these two tasks and getting a future back here. So now I'm saying run until complete this future. This future is done when both of the tasks I've gathered are done. Okay? So that will fix that problem. Okay, let's come on to the event loop itself, which we've been using. We've called a few functions on it, like create task and create future. But the API of the event loop is huge. I mean, it really is a kind of God class, really. It just does everything. So these are the kinds of things you can find in the event loop interface. Starting and stopping the event loop. Scheduling callbacks. These are not coroutines. These are just regular callback functions. We can arrange for them to be called at some point in the future. Factories that I've just told you shouldn't be using, because there are better alternatives. Configuration things you really need. There's more. There's a bunch of stuff for configuring our exception handling works. There's some methods for configuring diagnostics, debugging modes. There are methods for dealing with other asynchronous things like signals sent from the operating system. Sometimes I'm not going to go into these in detail today, I don't have time, but sometimes you do need to call blocking code from your async code. So what do? You can use a thing called the executor. So you can take some blocking callable and you can run it in the event loop using runIn executor. And there are different executors you can pass here. There's a thread pool executor and a process pool executor. So you can arrange for that function to be run elsewhere in such a way that your blocking function becomes non-blocking by being in another thread. And you can set the default executor. There's a bunch of low-level socket-level stuff, which we're not going to bother ourselves with today. And then there's this much higher-level protocol-level stuff. Create connection, create datagram endpoint, create Unix connection. We have some functions for watching file descriptors, adding readers, removing readers, adding writers to file descriptors, and also we can deal with pipes. So what is all this I/O stuff doing in the event loop? Right? Why do we need it in there? Well, okay, it is called async I/O, which is the hint, but why does it need to be in the event loop? So let's, in the last 10 minutes here, just put some I/O into async I/O. So I earlier built a very simple round-robin scheduler that just ran each task in turn. Okay? The secret sauce in async I/O is that it can schedule tasks on the basis of the availability or readiness of I/O, right? So the I/O-aware scheduler used in async I/O is a bit smarter. So as we clock around the tasks, run each one in turn, if we get to a task that the scheduler knows is waiting for I/O, we don't need to run it. We can skip it. We keep going around. If that I/O then becomes ready, we can go back and run that task immediately as the next task we run, so we don't have to wait very long. And then we can carry on round. Maybe we run that task. It blocks on I/O. The scheduler knows that. That I/O channel becomes available. The data's there. We can go back and get it immediately. So that's why all this I/O socket level stuff, pipe level stuff is in the event loop, in the scheduler. It's so that the scheduler can be aware and wait on I/O events using ePoll or select or whatever operating system features you have for async I/O at that lower level. Okay, let's click through these. So it would take me all day to go through all of this stuff in detail, so I'm not going to. I'll just show you this picture of the stack of abstractions that async I/O provides. And so we have seen suspendable and resumable functions, basically, concurrent functions, called coroutines and implemented in terms of generators, Python generators. We've seen the event loop, and tasks, which layers the notion of a task on top of that, and futures, so that we can wait for coroutines and get some sense of when they've finished. And also the event loops adds the ability to await sockets, file descriptors, pipes, etc. On top of that, we layer a thing called transports, which are provided by async I/O. And these basically encapsulate the notion of a communication channel which supports read and write. Okay, I'm not going to show you transports in detail. I'll show you them being used, but I won't show you how they work. On top of transports, async I/O allows us to implement a thing called protocols, which don't use coroutines at all. They're entirely callback-based approach to programming. I'll show you that in a moment. So that allows us to deal with callbacks that tell us when connections have been made or lost or data has been received, and we can respond to those events. And then on top of protocols, asyncio layers a thing called streams, which allows us to begin working with coroutines again. So if we don't like working in a callback style, we can go back to working in a coroutine style. So we have this huge stack, which is founded on coroutines, and all these higher level abstractions, and eventually we get back to working in coroutines. But at the top level, working at a much higher level of abstraction, the kind of behaviors we need to handle in our code. So I'm going to show you, we have 10 minutes, 9 minutes left, so I'm going to show you a quick example here of a chat server, right? Simple thing. So here's a chat room class. We initialize it with an event loop, and we give it a port, and we give the chat room a name. And this is the important thing here. We're going to manage a mapping, a dictionary for usernames, people in the chat room, to transports. And you're going to see these transport objects. They are things that we can read and write to. Okay? Read from and write to. When we run the chat room, it's going to call this method on the event loop called createServer. And createServer will invoke this callable, this factory function for each new connection to the chat room. Okay? So each time a connection comes in, it will invoke this thing, and it will create a thing called the protocol, which you'll see in a minute, with a reference back to the chat room. Okay? What else does the chat room have? Well, we have a way to deal with users arriving, register user. So we can only register the same user once in the dictionary. If it's a new user, against their username, we keep a reference to their transport, which is how we can communicate with that user, by writing to that transport. And we broadcast to the chat room user arrived. We can deregister a user when they leave. We can get a list of users by iterating through the keys of that dictionary. When a message arrives from a user, we can broadcast that to all of the users, prefixed with their username, so we know who it's from. And here's the broadcast. When we want to broadcast a message, we just iterate over all the transports and send the message with the correct line ending for telnet, which is what we're going to use here. So I said that every time a new connection is created, asyncio will instantiate one of our protocol objects. So here's the protocol object. So the server will instantiate this once for each connection with a reference back to the chat room. And it's extremely simple. There's basically this state machine, right? It's going to call connection made exactly once. It's going to call data received as many times as necessary, and it's going to call connection lost exactly once. It's very simple. So these three methods are really all you need to implement a asyncio protocol. It's very straightforward. So when a connection's made, I get a reference to the transport from asyncio. I write hello, welcome to the chat room name, and I ask them to enter their username. When I get data received, I have to decode that into a string, and then I push it into this accumulated lines thing, because I just get bits of data, right? They're not logical lines. I have to look for the line endings in that data as it arrives. So I iterate this function, which you'll see in a moment, just extracts lines of text from whatever data I'm getting. And then when I get a complete line, I pass it to this handle line. And when the user leaves, the connection is lost, I just deregister the user. Okay? You don't need to understand the detail here. This is just looking for lines of text in the data that comes in. And the very first thing I expect a user to enter is their username, because that's the first thing we ask them for. So if username is none, the first text they give us is going to be their username. Otherwise, we send a message from that user. What's interesting here is, of course, we might have 1,000 users in this room, and this simple code would handle thousands of users, no problem. We have shared mutable state here, right? But we don't have to worry about locking or any of that, because we know that only one of our coroutines is executing at any instant, right? So we've completely sidestepped the problem of the shared mutable resource in a concurrent system. All the code I'm showing you here looks completely sequential. It is completely sequential, right? It's the fact that we can suspend execution, and you can just assume that you have access to this. So as long as you're careful about when you're yielding control to the scheduler with your awaits, you can assume that you have exclusive access to any shared resource between those await statements. What you can't do is have an await in the middle of something where you have essentially kind of transactional behavior, which either must completely or not at all. So there we go. Register user, deregister user. There's a command to list users, and then we just write text to the transports to get things to show up. So that is that, and I'm just going to finish by showing you. So here is the chat server. Here's the chat room code. You can see it's quite concise. Here's the async IO protocol, which inherits from the base class in the library with the three methods I just showed you: connection made, data received, connection lost. Okay? So we can run this. That server's now running. And then I've got a couple of terminals here. I know you shouldn't use telnet, but it's convenient. There are no security people here, are there? So I'm going to telnet into my computer on port 1234, and you see, welcome to Chatterbox, enter your username. I am Sheila. Okay, user Sheila has arrived. In another session over here. Welcome to Chatterbox, Jim. And you see we get Jim has arrived. And then we can say, hi Sheila. There we go. Very simple, right? So nice concurrent behavior, multiple connections, no parallelism whatsoever, and efficient I/O. So I haven't tested it, but I would expect this to scale to thousands of concurrent connections without any difficulty whatsoever. And that, ladies and gentlemen, is it. Thank you very much. And I think I'm out of time, but I will take questions if you want. Yeah.
Is it possible that some operation tasks are striving during your scheduling? If your task is constantly became not wait, so it was waiting and now not waiting,
yeah,
the scheduler will return to this task, right?
That it will return to the task.
Yeah.
My understanding, well, it depends on the event loop implementation, right? So you can write your own event loop based upon the stuff that's in async IO. And async IO comes with different event loops. There's a reactor event loop and there's a proactor event loop. And you have to choose the event loop implementation you use depending on the scheduling qualities you want, right? So you actually have, in theory, complete control over what's going on because you could write your own scheduler. But in terms of the details of how it does that scheduling, I haven't looked very deeply into the rules. I mean, honestly, I've never needed to use anything but the default scheduler that Python gives me on the operating system I'm using. But underneath, it's just using calls to select or epoll to wait on file descriptors or sockets. Okay? I believe it's lunchtime or something. Okay, thank you very much.